All right, let's talk about greenhouse gases. But maybe not in the way you're used to. Before we get into any of the problems, we're going to look at them as a fundamental part of our planet, an invisible thermostat that literally makes life on Earth possible. Let's see how it works.
And to really get a handle on this, let's start with a little thought experiment. What if you could just snap your fingers, poof, and every last molecule of greenhouse gas vanished from our atmosphere? What do you think our world would feel like then?
Yeah, it would be a frozen wasteland, an ice ball. The average temperature of the entire planet would drop to about minus 18 degrees Celsius. That's 0 degrees Fahrenheit. Compare that to the pretty comfortable 15 Celsius or 59 Fahrenheit we have now. That huge difference is all thanks to this natural thermostat.
So first up, let's get into how this essential blanket actually does its job. Before we can even begin to talk about having too much of a good thing, we have to understand why it's such a good thing in the first place.
You know, the basic idea is actually really simple. The sun beams down energy, warming up the Earth. The Earth then tries to radiate some of that heat back out into space. A greenhouse gas is just a type of gas that's super good at catching that outgoing heat and bouncing it back down, keeping the planet toasty.
Now, here's what's truly wild. You'd think these powerful gases make up a huge chunk of our atmosphere, right? Not even close. 99% of the air we breathe is just nitrogen and oxygen. All those greenhouse gases we're talking about, they're crammed into that tiny little 1% slice. It's kind of mind-boggling how powerful their effect is.
And here are the main players. Now, water vapor is actually the biggest contributor, but its level is pretty much controlled by the temperature that's already set by the others. It acts more like an amplifier. So for that reason, the ones we're really going to focus on today are carbon dioxide and methane, because they have a much more lasting control over that planetary thermostat.
But okay, how do they do it? How do these specific gases trap heat when almost all of our atmosphere just doesn't? Well, the secret is all in their molecular structure. It's a tiny bit of physics, but the idea is actually pretty cool.
So here's the key difference. Nitrogen and oxygen molecules are simple. They're symmetrical. Heat radiation just passes right by them, doesn't even notice they're there. But greenhouse gases, like CO2, are built with different atoms, which makes them lopsided or asymmetrical. And that special structure lets them vibrate and dance when heat energy hits them, soaking it up and then firing it back out in all directions, including right back down to us.
And for an incredibly long time, we're talking millions of years, this whole system was in a state of equilibrium. The natural processes that released these gases were balanced by the processes that absorbed them. And it was this delicate, long-term balance that allowed life as we know it to flourish. But that balance has been broken.
Which brings us to the human fingerprint. Around 1750, the Industrial Revolution kicked off, and we started messing with this natural system at a speed and scale the planet had literally never experienced before.
And here's the bottom line. Since that time, human activities, mostly burning fossil fuels, have cranked up the amount of carbon dioxide in our atmosphere by more than 50% above what it was for millennia.
And if you think that's a lot, the story for methane is even crazier. Its concentration has exploded by over 150%. I mean, in a geological blink of an eye, we've grabbed Earth's thermostat and cranked the dial way, way up.
This timeline really puts the sheer speed of this into perspective. Look, it took 200 years for the first major jump in CO2. But then, it took only 56 years, less than a single human lifetime, for the next jump, which was 3 times bigger. The pace isn't just fast, it's accelerating. Okay, so we know CO2 and methane are the two big drivers here, but they don't operate the same way at all. They have completely different warming styles. And to compare them, scientists use a really helpful concept called global warming potential.
So GWP is basically a power ranking for greenhouse gases. It's a standardized score. Carbon dioxide gets a score of exactly 1, and then every other gas is measured against it. It helps us figure out the kind of punch these different gases pack and over what period of time.
And would you look at this? Over a 20-year window, methane is an absolute beast. It is over 81 times more powerful at trapping heat than the exact same amount of CO2. It delivers this massive, immediate warming shock to the system.
So this shows you the crucial trade-off. Methane is the powerful sprinter. It's incredibly potent, but it's short-lived, breaking down in about 12 years. Carbon dioxide, on the other hand, is the marathon runner. It's less potent pound for pound, but man, does it have staying power. Some of the CO2 we release today will still be warming our planet thousands of years from now.
And that brings us to the final and, let's be honest, the most important part of this whole story. We've overloaded the system. We've thickened that essential blanket.
So what are the actual consequences of breaking this delicate balance? What's at stake?
Well, the global scientific consensus, all bundled up by the IPCC, is pretty stark. If we stay on our current path, we are on track to blow past a warming level of 2 degrees Celsius, a point they officially call dangerous, sometime between 2040 and 2070.
And to steer clear of the worst impacts and stay below that more ambitious 1.5-degree target, the path they've laid out is incredibly clear and incredibly steep. Global emissions need to peak before 2025, and then they need to be slashed by nearly half by the end of this decade.
So look, we get the mechanism now. We can see the human fingerprint all over the atmosphere's chemistry and the accelerating change. We've basically taken apart the planet's thermostat, and we can see exactly which wires got crossed. The real challenge for all of us now is figuring out how we're going to fix it.